Hello everyone, myself Professor Ritesh Mahajan from Marathwada Mitra Mandal Institute of Technology, Lohagaon, Pune. So this is my second lecture based on the unit number 4. That is the unit number 4 is robot dynamics of robot and its motion planning and control. So in my last lecture, we had discussed the dynamics of robot, and in the dynamics of robot, we discussed the concept of forward dynamics and inverse dynamics of robot, as well as the approach to find out the the different types of joints and forces of the joint of the robot or the robot manipulator, that is nothing but the Euler-Lagrange's approach and Newton-Euler approach. So in this lecture we are going to focus on motion planning and control of the robot manipulator. So while defining the uh, different types of joint forces, torque, or whenever your robot manipulator will perform any kind of task, it has to travel from one point to another point, and that whenever it will travel from one point to another point, it has to follow certain path, and that following of that path by the robot manipulator is called as your trajectory planning or the trajectory motion planning. So here we are going to study the trajectory planning for the different types of your motion, robot motion. So the significance or the importance of this trajectory planning is as I said, in the application like plicantless robot, the spot welding, or any kind of application that may be assembly operation or manufacturing operation that will be carried out with the robot manipulator. So the robot manipulator have to move from one point to another point, and while moving from one point to another point will have this trajectory to define the path, and that is nothing but your trajectory planning. So first of all, we'll see the difference between what is the difference between the path and trajectory of your robot. So path is a sequence of robot configuration in particular order without respect to your time. So from one point to another point, you have defined one way, one path, but it is irrespective of the time, that is called as a path. But whenever that sequence of robot configuration, it travels from one point to another point, it is specified with respect to time, then that is called as a trajectory. So here suppose this is the robot manipulator ring ABC. It is traveling in some particular path. It may be following such parabolic curve. So whenever it is following only curve irrespective with respect to of time, or then it is called as a path, and whenever this path is a function of time, then it is defined as a trajectory. So simply when path is a function of time, it is called as a trajectory. To study the Cartesian and joint space trajectory, we have other different types of cases.
So different types of cases are nothing but joint space trajectory and a Cartesian space trajectory. So in the joint space trajectory, we are generally defining the position, velocity and the acceleration, while in Cartesian space trajectory, we are defining that parameter like position, velocity in Cartesian. In joint space trajectory, we are considering the angle of rotation. That means uh, in joint space trajectory, the revolutionary movement of, or you can say that in joint space trajectory, the position, velocity and the acceleration is a function of theta with respect to time. But in Cartesian space trajectory, you are getting the there are linear displacement, linear velocity and acceleration. These are nothing but the functions of time.
By using this condition, theta dot of
Now,
0
now,
is 0.
now here there are the different cases of the trajectory planning for cubic polynomial. So as I discussed in the last slide, uh, that we have the joint space trajectory and we have the Cartesian space trajectory. So for the joint space trajectory, we had considered here, and for the joint space trajectory, uh, whenever the displacement or your robot end effector that will follow a cubic polynomial core as shown in this particular figure, then we'll try to find out their particular angular acceleration and angular velocity plot with respect to time. Now, how to find out this particular uh, plot of angular velocity and angular acceleration? So for that we have the equation of cubic polynomial, that theta of t is equal to a0 plus a1t plus a2t square plus a3t cube. Now this equation is nothing but the define the angular displacement of your robot manipulator, and that is the function of time t. Now here it is the case 1 that we are discussing. So in the case 1 it is given that initial and final velocities are 0. So initial and final velocities means what? The theta dot of 0 is 0 and theta dot of tf is 0. So with this condition, to find out the trajectory or the path velocity profile, angular acceleration profile, we need to determine the values of this a1, a2 and a3 and a0. Now let us will discuss how we can determine these values.
So if I substitute theta dot of 0, so this equation is 0 a1 plus t0 t0. So a1 is equal to 0 I'll got. Now remaining two equations I can solve for the values of theta f. So I'll get these values of a0 equal to theta 0, a1 equal to 0, a2 is equal to 3 by tf square in bracket difference between final and initial angle, while a3 is equal to minus 2 upon tf cube difference between final and initial angle. So these four unknowns that we have find out from this particular equations. So while solving the numericals, you will have given the value of theta 0, theta f and the time span. So you will have to compute that a0, a1, a2, a3. Once you have computed a0, a1, a2, a3, we can substitute their value in this equation 7.4 and the equation 7.5. So you can calculate the values of theta of t, theta dot of t and theta double dot of t for various instant of time. So this expression, this values of a0, a1, a2, a3, that you have to remember, and based on that, then that is useful to solve the numerical. Means whenever in case of numerical, you will have to define the trajectory for displacement, velocity and acceleration. At that time, first of all, with the help of this constant, you can define the equation in terms of t, and you can find out the values of theta, theta dot of t and theta double dot of t for different values of the time. So this is the first case that we have seen. So this is the solution. That means the values of a0, a1, a2, a3, whenever the initial and final velocities are assumed to be 0, then and only will have to use this particular expression to solve the numerical. Now the next case 2, trajectory planning for cubic polynomial when initial and final velocities are non-zero. So whenever the initial and final velocities are not 0, so in earlier case theta dot of 0 that we have considered as 0 and theta dot of tf that is also we have considered as 0. But here that final and initial velocities are non-zero value, and with this non-zero value the cubic polynomial equation that in that by using that conditions, now we can find out the value of a0, a1, a2 and a3. So that values that becomes a0 is equal to theta 0, a1 is equal to theta dot of 0. In earlier case it is equal to 0, but here in this case it is theta dot of 0, while a2 is equal to 3 upon tf square minus of in bracket of theta f minus theta 0. So this expression is same, but minus 2 upon tf theta dot minus 1 upon tf of theta dot of f, while a3 this term minus 2 upon tf cube theta f minus theta 0 plus 1 upon tf square theta dot of f plus theta dot 0. So these two terms in this a2 and a3 value, these terms are get added when the final velocities are not 0. Initial and final velocities are not 0. As in earlier case, we can able to find out the values of theta t, theta dot of t and theta double dot of t for the two different path, like say you can say through via point. So
So here via point terminology is discussed. In the via point terminology, instead of considering the initial and final points, we have considered the intermediate point like theta A, theta B, theta C and theta D. So with this particular point, we can determine the trajectory like this. So for that, we have to determine, suppose we have considered the point theta 0 and theta B via theta, we are considering this trajectory from theta 0 to theta b via point A. So for the theta 0 to theta a, we have time span t0 to ta, and from theta a to theta b, we have the time span is equal to ta to tb. So with this, we can write the trajectory equation. To trajectory equation, first cubic is nothing but theta of t is equal to a10 plus a11t plus a12t t square plus a13t cube, while second is theta of t is equal to a20 plus a21t plus a22t square plus a23t cube. So here simply uh, the coefficient for the different two cubic uh, functions that we'll have to define. So here we'll have to find the values of a1, a10, a11, a12, a13 and a20, a21, a22 and a23. So by applying the conditions, we got the 8 equations and 8 unknown. So with these 8 equations and 8 unknown, we got the value of theta a10 is equal to theta 0, a20 is equal to theta v, while a11 is equal to 0.
directly we will solve the numerical.
And the remaining one like a12, that will got with the help of this expression. So simply whenever the via points are given, we'll have to compute the values of coefficient a10, a11, a12, a13, a20, a21, a22 and a23 with the help of this expression. So here the theta v that we are getting, that is nothing but the via angle, while theta z is the final angle and theta 0 is the initial angle.
Here in this case, uh, the first case, based on the first case, first of all we will do the numerical. The second joint of SCARA manipulator is required to move from a to 30 degree to 150 degree in 5 seconds. Find the cubic polynomial to generate the smooth trajectory for the point. What is the maximum velocity possible for this trajectory? So in this case, uh, we'll consider that here it is not mentioned that what are the initial and final velocities that we have to consider, but here if we'll assume the initial and final velocities are 0, and for cubic polynomial we'll use the equation for case 1. So simply here, as far as the given data is concerned, 30 degree to 150 degree, so initial angle is theta 0 is 30 degree given and final angle is given as 150 degree, while the time tf is given as a 5 second. Now consider, as I said, the SCARA manipulator has a cubic trajectory. So the equation of the cubic trajectory, that theta of t is equal to a0 plus a1t plus a2t square plus a3t cube. That will be equation number 1. And as we have seen in the last slide, we can find out the value of a0, a1, a2 and a3. So the value of a0, that is defined at theta 0, and value of a1 is 0. So with this values, now we can rewrite the equation number 1, and that equation number 1 becomes theta 0 plus a2t square plus a3t cube. Now again, we know we are already defined the value of a2 and a3 by using this relation. So by substitute the given, we know the value of theta f as well as theta 0. So substituting this value, and we'll get the value of A2, that is 14.4. Similarly, the value of A3 is we are getting as a minus 1.92. Now with this value here we got all these values of A0, A1, A2 and A3. Now with these values that I will substitute in the equation number 2. So the equation number 2 becomes the theta of t is 30 plus 14.4 t square minus 1.92 t cube. So this is the expression for position trajectory. Now let it take the derivative with respect to time t for this equation number 3, that becomes 28.80 minus 5.76 t square. So the equation 3 and 4 define the displacement and velocity cubic trajectory for the given SCARA manipulator. Now here we have to find out where, at what point the maximum velocity you will getting. So for that, as we got the values of we got the generalized expression for displacement and velocity, we can find out the values of displacement and velocity for different values of time, say from 0 to 5. So in the next slide here, by using that equation, we have find out the value of theta of t and theta naught of t for the different value of theta, say 0, 1, 2, 3, 4, 5. So I got these values, and simply I will plot the graph of theta of t versus time. So I will got this trajectory, which is the simply a straight line with some initial value of the theta angle, that is 30 degree. Now when I plot the values of velocity, so at the values of, say, time is equal to 2 and time is equal to 3, the values is same. So I am getting this as a parabolic curve, and through this I can say at this point this is the Vmax, or you can say maximum velocity. At this particular angle the maximum velocity will take place. So if I want to find the maximum velocity, so that time is nothing but, I can say, at the middle portion of this particular parabolic curve for the velocity profile, that I'll get the value of the time, that is nothing but 2.5 second, and if I substitute this value, so it becomes 36 degree. So 36 degree per second is the value of maximum velocity at the point 2.5 second. So whatever the assumptions that you have made, that is the final initial velocities are zero, that now that can be verified after plotting the graph, and we can say whatever the joint angle and the velocity angles that we have defined, that is the correct. So in this case, you have such a case of numerical, you have one cross check point. Suppose whenever you are solving the values of theta of t, so if the values of theta at 0 and theta of f, it matches with the given value 30 and 150, so your calculated values are correct.
Now, in the next lecture, I will discuss two or three more numerical based on this particular terminology. Thank you.